In this video, I want to go over 3 identities that you need to know if you're going to work in the unsaturated zone or the soil zone. So the first identity is the relationship between the metric potential, psi, and the metric suction, which I usually give with the symbol absolute value of psi. For example, here's a typical soil moisture characteristic curve diagram. You've seen lots of these. The x-axis is soil moisture content, and on the y-axis, in this case, I plotted the metric suction. So once again, potential is the symbol, metric potential is the symbol psi, metric suction has the symbol absolute value of psi, and that's the relationship. The suction is merely the negative value of psi. Psi is always less than 0. It's always a negative number. The absolute value of psi, therefore, is always, and absolute values are always greater than 0. So the suction is simply the positive value of the potential. So for example, if the metric potential is equal to negative 2.5 meters, then we can very quickly say that the metric suction is equal to positive 2.5 meters. That's all there is to it. Metric potential is negative. Metric suction is the same value, but positive. Now, the second important relationship has to do with the relationship between the metric potential psi and the water pressure, the gauge pressure P. So let's review a little bit about the relationship between head and pressure and psi. So here we have a cross-section of the earth. There's my little tree here. And I've got 2 piezometers inserted into the ground. The water table is the line separating the blue area, which is the saturated zone, and the gray area above, which is the soil or the unsaturated zone. And the first piezometer goes into the saturated zone, where you remember that the water is under positive pressure. And under those conditions, water in the ground will press into the piezometer and lift it up into the piezometer, and water will rise in the piezometer. We define the head as the elevation of that water in the piezometer above the datum. So in this case, the head would equal this distance here, this length there. And further, remember that we can break this head into 2 components. The first represents the elevation of the entry hole in the piezometer above datum, and we call that Z, the elevation of that point we're interested in. And the second is the height of the column of water, which we call the pressure head, H sub P. The pressure head is a real number. It's a positive value. And so we can write that the head, this is in the saturated zone, that the head is equal to elevation Z plus the pressure head. Now, to the right, I've inserted a tensiometer into the unsaturated zone, which is exactly the same thing. So I insert a tube with an opening at the bottom, and everything else is the same. So the elevation here above datum of the entry port in the tensiometer is given by Z. The difference now is that the water in the unsaturated zone is at a negative pressure. So it's not going to come out of the ground and push water into the piezometer. In fact, what it will do is it will suck water. If I were to put it into the tensiometer, it would suck that water out of the tensiometer into the ground. So we don't have any physically visible and measurable height of a column of water. And for that reason, but we can still calculate what that amount is. It's called the pressure head in the unsaturated zone. And because it's not something physical we can see, we give it a different symbol. So in the unsaturated zone, we write that the head is equal to the elevation Z plus psi, where psi is the pressure head in the unsaturated zone. In both cases, however, we want a relationship between the actual water pressure P and the pressure head, which is psi in the unsaturated zone, or I'll put right over here, remind you, it's the same thing as the pressure head in the saturated zone. And that relationship is really important, and you need to learn it. And that is that the pressure head in the saturated zone, or the psi in the unsaturated zone, is related to the pressure by the following equation. Psi equals the gauge pressure P divided by rho, the density of the water, times G, the gravitational acceleration. Or if I wanted to rearrange this equation to solve it for P, I could write as well that the pressure, the gauge pressure P is equal to rho times G times, in the unsaturated zone, psi. So let's see how this works. So for example, if I had a psi in the unsaturated zone of -2 meters, that is equivalent to a pressure that would be equal to the density of water, which for fresh water is 1,000 kilograms per meters cubed. You can essentially treat that as a constant since we're almost always working with fresh water, times the gravitational acceleration, 9.81 meters per second squared at the surface of Earth. That again is a constant, times -2 meters, which is psi. And if I do that multiplication, I get negative 19,620 pascals. So saying that the metric potential is -2 meters is equivalent to saying that the pressure of the water is minus 19,620 pascals. That is an identity. You're saying the same information different ways. You can either express the pressure of the water or the pressure of the water in terms of its pressure in pascals, or you can express it as a length equal to its pressure head, or in the unsaturated zone, its metric potential. Now, the third important relationship, identity here, you need to understand in the unsaturated zone is the relationship between the moisture content of a soil and the metric potential of the soil, or metric suction, as I've actually plotted up here. And that is given by that particular soil's soil moisture characteristic curve. So I've shown a particular soil moisture characteristic curve in this diagram, and that's the blue line. This gives the connection between the moisture content of a soil and the pressure of that water, or rather the metric potential of that water for any moisture content. For example, let's say in this particular soil described by the blue line, that I find that the moisture content is 0.3. Okay, saturation is 0.42, so this soil is not fully saturated with water. There's some air present as well. And when the moisture content is 0.3, according to the soil moisture characteristic curve, if I go and read off the value here, that looks like 1, 2, 3, right? So that's 3 meters of suction. So at a moisture content of 0.3, the metric potential will be -3 meters. And that is an absolute equivalence, that it must always be true. If the soil moisture content were 0.1 over here, then I would expect to find that that water would have a metric potential of, it looks like about -70 meters. The metric potential would be -70 meters. That again is a one-to-one correspondence. So notice too, because I know the relationship between the metric potential and pressure, I can also answer questions like, well, if the moisture content of the soil is equal to 0.2, what's the pressure of the water in the soil? Let's see if we can figure that out. If the moisture content is 0.2 by the soil moisture characteristic curve, I go up here like this, right? That tells us that the metric, in this case, suction, is about 12 meters. That's the metric suction. So I'll write that down. The metric suction is 12 meters. The metric potential, using the first of these relationships here, right, will be -12 meters. And the pressure of the water will be equal to, I'll have to multiply it out using this relationship here, will equal 1,000 kilograms per meter cubed, the density of water, times 9.81 meters per second squared, times -12 meters. And that would give me a pressure of about -118,000 pascals. That would be the pressure of the water at a moisture content of 0.2. There you go. So again, the three relationships you absolutely know how to need to work with. The first one's super easy. Metric suction and metric potential, it's the same value, it's just the sign. If it's potential, it's negative. If it's suction, it's positive. The second relationship, super important, is the relationship between the metric potential and the water pressure, always given by this relationship or in the rearranged form over here. And the third relationship is the relationship between the moisture content of a soil and the metric potential of the soil, which is always given by its soil moisture characteristic curve.